Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with earthquake lights, the mysterious glow before the ground moves. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried, atmospheric journey through the wonders of the cosmos. Your mind is quiet, the universe is vast, and we are ready to explore. This phenomenon, known as earthquake lights, presents an intriguing intersection of geology and atmospheric science. Often observed shortly before or during seismic events, these luminous manifestations can vary in appearance, ranging from bright orbs to flickering glows. Their unpredictable nature raises questions about the mechanisms responsible for such displays. Research suggests that these lights may originate from the piezoelectric effect, which occurs when stress is applied to certain crystalline materials found in the Earth's crust. This stress can generate electric charges, leading to ionization of air molecules, creating glowing plasma. The specific conditions under which these lights appear remain a topic of scientific investigation, with some theorists proposing that geological and atmospheric factors may converge to produce the observed luminosity. The significance of earthquake lights extends beyond mere curiosity. Understanding their occurrence could enhance predictive models for seismic activity. By correlating these lights with tectonic movements, researchers aim to refine early warning systems, potentially saving lives and mitigating damage. This phenomenon serves as a reminder of the complex interactions between geological forces and atmospheric conditions. As research progresses, deciphering the origins and implications of earthquake lights may unveil deeper insights into the dynamic nature of our planet. Such understanding underscores the importance of interdisciplinary studies in unearthing the mysteries of Earth's geophysical behavior. Historical records provide intriguing accounts of luminous phenomena preceding seismic events. In ancient times, civilizations observed unusual lights flickering in the sky, often attributing them to divine intervention or omens. Various cultures documented these occurrences, noting that they frequently appeared moments before the earth trembled. These observations become a part of folklore, blending the realms of science and mythology. As early societies sought explanations for the unpredictable nature of their environment. In the late 18th century, the phenomenon began to attract the attention of scientists. Reports from Europe and North America described glows resembling flames or bright arcs, shimmering against the backdrop of darkened skies. These sightings were often dismissed as mere superstition until detailed accounts began to surface, particularly around notable seismic events. The phenomenon has been recorded during significant earthquakes, with witnesses reporting hues of blue, white, or even red illuminating the horizon. Such descriptions emerged from various regions, revealing a pattern that suggested a correlation between these lights and tectonic activity. The scientific community gradually recognized these accounts, leading to systematic studies. By the early 20th century, researchers began to analyze the atmospheric conditions surrounding these luminous events, seeking to understand the relationship between electrical activity and tectonic movements. These explorations laid the groundwork for future investigations into the enigmatic nature of earthquake lights. Earthquake lights are luminous phenomena that occasionally appear in the sky prior to seismic activity. Documented over centuries, they manifest in various forms, including glowing orbs, streaks, or even bursts of light. The exact mechanism behind these occurrences remains elusive. Though multiple hypotheses have emerged, they are often reported in conjunction with tectonic strain, suggesting a possible connection between geological stress and atmospheric effects. Research indicates that these lights may be related to the release of electrical charges generated by the fracturing of rocks. As tectonic plates shift, the intense pressure may cause piezoelectric effects, where certain materials emit an electric charge under mechanical stress. This process could lead to ionization in the atmosphere, resulting in visible light phenomena. The spatial distribution of earthquake lights tends to coincide with regions of active fault lines. Observations have been reported globally, with varying characteristics depending on local geology and atmospheric conditions. The transient nature of these lights often makes them difficult to study, as they may last only a few seconds to several minutes. Despite the ongoing research, definitive scientific consensus remains elusive. Continued exploration into the properties and causes of earthquake lights may provide insights into both seismic activity and the underlying physics governing such atmospheric phenomena. Understanding this relationship could enhance predictive models and deepen our knowledge of Earth's dynamic systems. The geological conditions leading to the phenomenon known as earthquake lights stem from the intense stresses generated within the Earth's crust. Fracturing rock, subjected to immense pressure, releases energy in the form of electromagnetic fields. These fields can interact with the surrounding materials, producing a variety of luminous effects prior to seismic activity. In certain instances, gases such as radon may also become charged during the fracturing process, contributing to the illumination. When these charged particles interact with one another or with the Earth's surface, they may manifest as brilliant flashes or persistent glows. This region, where tectonic plates converge or diverge, often serves as a hotspot for such occurrences, revealing the dynamic nature of the Earth's crust beneath the surface. Studies indicate that these lights can appear minutes to hours before an earthquake. Though their visibility is contingent upon local conditions and atmospheric clarity, they may vary in color and intensity, offering a unique glimpse into the complex interplay of geological forces. The scientific community continues to explore the specific mechanisms behind these lights, as they not only signify impending seismic events, but also provide valuable data regarding the stress accumulation within fault lines. Unraveling this connection may not only illuminate the causes but also refine the broader understanding of tectonic processes. Categories of earthquake lights reveal a diverse array of phenomena, each characterized by distinct visual attributes and contexts. Glowing orbs, often reported as spherical or oval, can hover or dart above the ground, frequently observed in the moments preceding seismic activity. These luminous shapes may vary in color, with shades ranging from white to bluish hues, illuminating the darkened landscapes in an eerie glow. Flashes are another manifestation, typically described as brief and bright bursts of light, reminiscent of lightning yet occurring in serene conditions. This phenomenon is often brief, lasting only a fraction of a second, yet it can leave a lasting impression on those who witness it. Another category encompasses the broader atmospheric phenomena, such as glowing clouds or shimmering skies, which can appear as a result of electrical discharges in the upper atmosphere. These displays often coincide with the onset of seismic movements, hinting at an intrinsic connection between tectonic stress and atmospheric electricity. Reports from various regions suggest that these lights may not be limited to a particular geographical area or seismic event. They have been documented in both minor tremors and significant earthquakes, underscoring the complexity of these interactions. Understanding these categories may provide valuable insights into their underlying mechanisms and their implications for earthquake prediction. The role of piezoelectricity in earthquake lights highlights a fascinating intersection of geology and physics. Certain minerals, such as quartz, exhibit piezoelectric properties. They generate an electric charge when subjected to mechanical stress. This phenomenon occurs when tectonic forces build up in the Earth's crust, creating strain in rock formations. As stress accumulates, microscopic movements within these minerals produce electrical discharges. These discharges may manifest as luminous phenomena in the atmosphere, observed prior to seismic activity. The energy released could ionize surrounding air, resulting in the generation of light. This region, where the crustal stress is highest, often becomes a focal point for such phenomena. The light itself can appear in various forms, ranging from bluish glows to flickering flashes, each reporting a unique interaction between geological forces and atmospheric conditions. Research into this connection is ongoing, with scientists investigating specific patterns and conditions under which these lights occur. Current hypotheses suggest that the spatial distribution of piezoelectric minerals and their alignment within fault lines may influence the intensity and frequency of these luminous events. Further exploration may enhance understanding of the mechanisms driving these lights, providing potential advancements in earthquake forecasting and risk assessment methodologies. This intriguing relationship underscores a deeper connection between Earth's materials and the atmospheric displays they can produce. Historical records reveal notable instances of this phenomenon, where luminous displays were observed prior to significant seismic events. One prominent case occurred in 1868, just before the powerful Hayward earthquake in California. Eyewitness accounts detailed glowing orbs and flickering lights illuminating the night sky, an occurrence that perplexed both locals and scientists alike. Another significant event took place in 1931 in the region surrounding the Kanto earthquake in Japan. Witnesses reported brilliant flashes of light emanating from the ground, accompanied by an eerie silence that enveloped the area. This mysterious glow persisted for several minutes, shortly before the tremors shook the city of Yokohama. In 1999, as the Izmit earthquake struck Turkey, residents observed various forms of luminescence. Some described a bluish glow rising from fissures in the earth, illuminating the surrounding landscape in an otherworldly hue. These accounts have spurred interest in understanding the mechanisms behind such phenomena and their potential predictive value. Scientific investigations continue to explore these incidents, examining the geological and physical conditions that may give rise to such atmospheric anomalies. Analysis of these case studies provides valuable insights into the complex interactions between geological activity and atmospheric phenomena, inviting further inquiry into the nature of Earth's dynamic processes. Cultural interpretations of luminous phenomena prior to seismic events reflect humanity's attempts to comprehend the unknown Feshig. Numerous societies have woven these glowing occurrences into their folklore and mythologies, attributing them to divine messages or omens. In various traditions, it is believed that these lights signify impending danger, serving as a warning from higher powers or spirits inhabiting the earth. Legends from regions prone to seismic activity often describe the lights as the spirits of ancestors or guardians, illuminating the path for the living. Certain Native American tribes view these phenomena as manifestations of the Earth's spirit, signaling a need for respect and attentiveness to nature's rhythms. In Japanese culture, similar beliefs exist, with terms like inazuma, referring to the lightning-like flashes seen before an earthquake. This association reflects a deep cultural understanding of the Earth's volatile nature. Such interpretations have shaped local responses to earthquakes, often leading to rituals intended to appease the forces believed to be at play. The narratives surrounding these lights serve not only as cautionary tales, but also as a means of fostering a connection between communities and their environment. These stories echo through generations, emphasizing the shared human experience of grappling with nature's unpredictability and the quest for understanding amidst chaos. Various luminous phenomena have been documented in the vicinity of seismic activity. Earthquake lights, often reported as bluish or white glows, are distinct from other atmospheric manifestations such as auroras or lightning. The specific conditions leading to these lights involve the piezoelectric effect, wherein stress and strain in certain geological materials generate electrical charges. This process creates a unique electromagnetic field, resulting in visible radiance prior to seismic events. Field dust auroras arise from solar wind interacting with the Earth's magnetic field, producing colorful displays high in the atmosphere. Their ethereal beauty is tied to solar activity, not tectonic movements. Lightning, on the other hand, is a product of atmospheric conditions characterized by electrical discharges during storms. These phenomena differ in origin, appearance, and the contexts in which they occur. Environmental factors such as humidity and temperature can influence visibility, often obscuring these elusive lights. Observations have been recorded in various settings, from rural landscapes to urban environments. Yet the witnesses often describe a fleeting, transient quality. These lights typically appear moments before the seismic tremors, creating an eerie prelude to the ensuing chaos. The scientific community continues to investigate these occurrences, seeking to establish a clearer understanding of their mechanisms and implications for earthquake prediction. Theoretical frameworks suggest that gas discharge may play a pivotal role in the phenomenon of earthquake lights. A prevalent hypothesis proposes that stress accumulation in geological materials can lead to the release of gases, particularly radon, prior to seismic events. This region's tectonic shifts create fractures, allowing radon gas to escape into the atmosphere. Once released, the gas may interact with the surrounding air molecules. Ionization is another critical aspect of this framework. Under heightened pressure conditions, the interaction between radon atoms and the surrounding environment can generate charged particles. These ions can then lead to a cascade of electrical discharges, creating the observed luminous effects. This process occurs in conjunction with the buildup of stress in fault lines, a precursor to significant seismic activity. The luminous displays could manifest as glowing orbs or streaks, often reported in various colors. These phenomena can appear in a variety of settings, typically in areas with significant geological activity. Observations have noted these lights occurring just before major earthquakes, reinforcing the connection between gas discharge and seismic events. Investigations continue to explore additional atmospheric factors, such as humidity and temperature, that may influence the visibility and intensity of these lights. Understanding these elements is crucial in refining predictive models and enhancing safety measures in earthquake-prone regions. The relationship between rock stress and the emission of light remains an enigmatic area of study. As tectonic plates shift and the Earth's crust experiences strain, the internal structure of rocks becomes altered. This stress accumulation often leads to microfractures, which can release energy in the form of luminescence. The mechanisms behind this phenomena are still being explored, with researchers investigating various mineral compositions and their responses to stress. In regions where seismic activity is prevalent, the presence of quartz and other piezoelectric minerals contributes significantly to light emissions. Under pressure, These minerals generate electric charges, which can manifest as visible light when fractures occur. Observations have recorded this luminous phenomena occurring moments before significant tremors, suggesting a possible precursor to seismic events. The spatial distribution of these light emissions varies, often correlating with fault lines and areas of known geological instability. This region serves as a reminder of the complex interplay between physical processes beneath the surface and the observable effects on the environment. Studies are increasingly focusing on monitoring these emissions in real time, aiming to establish a reliable connection between light phenomena and impending seismic activity. Understanding this relationship could lead to enhanced predictive capabilities. Yet the empirical evidence surrounding earthquake lights remains elusive. Various instruments have been deployed to detect these phenomena. Geophysical sensors, such as seismographs, capture the seismic waves that precede earthquakes, while electromagnetic field meters often record anomalies that may coincide with these lights. High-resolution cameras and infrared sensors offer visual documentation, capturing fleeting glimpses of the luminescence reported by witnesses. These devices, stationed strategically near tectonic boundaries, aim to correlate light occurrences with seismic activity. This region's unique geological characteristics contribute to the complexity of detection, as variations in rock composition and stress levels influence the manifestation of these lights. Data from satellite imagery has also been utilized, providing a broader perspective on light emissions across vast areas. Advanced analytics comb through these datasets, searching for patterns that may predict future events. The challenge lies in the sporadic nature of the phenomenon. Consistency in readings is often difficult to achieve. In tandem with these technologies, field studies involving direct observation play a critical role. Geologists and researchers meticulously document conditions leading up to seismic events, striving to establish a definitive link despite advancements in instrumentation. The quest for understanding earthquake lights continues, a mystery hovering like a faint glow before the ground shifts. Seismic activity serves as a foundational element in the emergence of earthquake lights. These phenomena are often observed in conjunction with tectonic movements, particularly in regions with significant geological stress. Observations suggest that the buildup of pressure within the Earth's crust may generate electrical charges. This release of energy, when coupled with the fracturing of rocks, can lead to the luminous displays noted by witnesses prior to seismic events. The precise mechanism behind this illumination remains elusive. Some researchers propose that frictional heating during the displacement of crustal materials might ionize local atmospheric gases, producing visible light. Others speculate that the piezoelectric effect, which occurs when certain minerals generate an electrical charge under stress, contributes to this phenomenon, offering a plausible connection between geological forces and energetic emissions. In areas prone to earthquakes, these lights can manifest in various forms, from soft glows to more intense flashes. Their appearance often coincides with minor tremors or impending larger seismic events. Reports vary significantly, with eyewitness accounts capturing a range of colors and shapes, expanding the intrigue surrounding these occurrences. The sporadic nature and brief duration of earthquake lights only add to the enigma, leaving scientists to unravel the complexities of this natural phenomenon. Amidst the rhythmic patterns of tectonic activity, the complexities of earthquake lights stand in contrast to other natural electric phenomena, distinct from more commonly understood occurrences, such as lightning or auroras. These lights exhibit unique characteristics tied to geological stress. While lightning is a product of atmospheric conditions, featuring rapid discharge of electricity in clouds, earthquake lights emerge from the Earth itself, possibly through piezoelectric effects generated in certain minerals under pressure. What these contexts, the potential sources of these enigmatic glows, have sparked considerable interest. Some researchers propose that the fracturing of rocks during seismic activity releases trapped gases, which may ionize and produce visible light. Comparisons with other natural phenomena reveal that while auroras result from solar wind interacting with the Earth's magnetic field, the mechanisms behind earthquake lights remain less understood and more elusive. The spatial distribution of these lights often aligns with fault lines, indicating a localized origin tied to tectonic movements. This relationship strengthens the hypothesis that they serve as a precursor to seismic events. Observations are rare and often anecdotal, making systematic study challenging. Ongoing research continues to examine the environmental conditions that lead to their manifestation, underscoring the need for a precise understanding of the interplay between geological forces and electrical phenomena. These observations may reveal a deeper connection between groundwater levels and the occurrence of seismic activity. Fluctuations in groundwater can alter the stress distribution within fault lines, affecting the movement of tectonic plates. This dynamic interplay creates an environment ripe for the manifestation of earthquake lights. The subtle shifts in pressure and the availability of water can influence the electrical properties of the surrounding rocks. When underground water is displaced by geological shifts, it can generate electric fields through piezoelectric effects. These electric fields may interact with the Earth's magnetic environment, potentially leading to the ionization of air particles. The result can be the stunning display of luminescence seen before seismic events. It is a phenomenon that eludes precise understanding, yet it underscores the complexities present in this region. Studies conducted in areas with high seismic activity have noted a correlation between changes in groundwater and the emergence of these lights. As water levels fluctuate, the subsequent changes in electromagnetic fields may provide crucial clues. This relationship suggests that monitoring groundwater could serve as an early warning system for impending earthquakes. Understanding these connections deepens the scientific inquiry into the mechanisms that govern both groundwater dynamics and the behavior of the Earth's crust, opening new avenues for research into predicting seismic events. Insights from tectonic settings reveal distinct regions where these phenomena manifest. These areas often correspond to geological boundaries, where tectonic plates interact under immense pressure. In regions classified as convergent, such as subduction zones, the strain accumulates over time, creating a perfect environment for unusual atmospheric occurrences. Here, the friction between plates can generate electric charges, giving rise to the glowing lights observed prior to seismic activity. Transform boundaries, characterized by lateral sliding motions, also contribute to the appearance of earthquake lights. The San Andreas Fault in California serves as a prime example, with its complex interactions producing not only significant quakes, but also sporadic bursts of luminescence. Observations in this region underscore the correlation between geological stress and atmospheric phenomena, suggesting a direct link between the Earth's movements and the light displays. In tension zones, where plates pull apart, such as the East African Rift, similar phenomena are documented. The volcanic activity in these areas may enhance the likelihood of visible emissions. Investigations into these regions continue to provide essential data, supporting the hypothesis that specific geological configurations foster the occurrence of earthquake lights. The ongoing research aims to clarify the underlying processes, enhancing the understanding of both tectonic activity and its atmospheric implications. These insights pave the way for a more comprehensive view of the interconnectedness of Earth's systems. The influence of magnitude and depth on light visibility reveals complex interactions between seismic activity and atmospheric conditions. Smaller earthquakes, often registering below a magnitude of 4, may not produce visible lights. In contrast, larger events, particularly those exceeding a magnitude of 6, have shown a higher propensity for generating luminous phenomena. This correlation suggests that increased energy release can amplify the conditions necessary for light manifestation. Depth plays a significant role as well. Shallow earthquakes, occurring at depths less than 10 kilometers, tend to be more associated with the appearance of lights. These events allow for a greater release of energy closer to the surface, facilitating the interaction with atmospheric particles. Deeper seismic events, on the other hand, often lack the same visibility. The energy dissipates over distance, reducing the likelihood of atmospheric excitation required for light phenomena. Regional geological features further influence these occurrences. Areas rich in tectonic activity, such as fault lines and volcanic regions, may enhance the visibility of such lights. The composition of the ground, its mineral content, and the presence of water can also affect how energy is released and how it interacts with the atmosphere. This interplay creates a dynamic environment where light visibility is not solely a function of magnitude and depth, but rather a complex synthesis of multiple geological and atmospheric factors. Earthquake lights have long intrigued researchers seeking reliable prediction methods. These luminous phenomena often occur shortly before seismic activity, leading to speculation about their potential as precursors. Various theories suggest that the fracturing of rocks and the release of gases may generate electrical charges, manifesting as visible light. In this region, the occurrence of these lights could serve as a subtle warning sign, hinting at impending geological shifts. Monitoring these emissions allows for a deeper understanding of their relationship with tectonic movements. Some studies indicate that specific atmospheric conditions may enhance their visibility, potentially providing crucial data for early warning systems. The challenge lies in distinguishing these lights from other atmospheric phenomena, such as auroras or lightning, which can obscure the signals of seismic activity. Observation locations with a history of earthquake lights have revealed patterns, suggesting that these events might not be random but rather linked to particular geological features. The correlation between light emissions and subsequent tremors invites a careful analysis of data collection methods and predictive algorithms. Integrating knowledge about these phenomena into existing earthquake prediction frameworks could enhance preparedness efforts. Ongoing research aims to refine our understanding of the conditions that lead to the emergence of these lights, potentially transforming them into a valuable tool for mitigating seismic risk in vulnerable regions. The 2011 Tohoku earthquake exemplifies a significant event where unusual atmospheric phenomena were reported prior to ground movement. In the days leading up to the magnitude 9.0 quake, witnesses described a series of luminous displays, often described as bluish or whitish glows, illuminating the sky. These occurrences were documented in various locations, drawing attention to their potential correlation with seismic activity. The phenomenon was observed in conjunction with the tectonic shifts occurring beneath the Pacific Plate as stress accumulated, and, in analyzing these observations, scientists examined geological data and atmospheric conditions, seeking to establish a connection between the physical properties of the Earth and the electromagnetic emissions possibly related to the stress of impending seismic events. Understanding this relationship may aid in better forecasting techniques. contributing to early warning systems that could save lives in future occurrences. The exploration of these lights continues, shedding light on the complex interactions between geology and atmospheric phenomena. Eyewitness accounts from the 1906 San Francisco earthquake reveal an intriguing correlation between seismic activity and luminous phenomena. Reports frequently mention a brilliant glow illuminating the sky moments before the ground trembled. Observers described a bluish-white light, often likened to electrical discharges, playing across the horizon, casting an eerie illumination over the city. These accounts came from a diverse range of individuals, including residents, firefighters, and even scientists. Many noted the lights flickering above buildings, while others reported them appearing as streaks or orbs hovering in the air. The illumination seemed to pulsate, synchronizing with the mounting tension felt in the atmosphere prior to the catastrophic shaking. Some eyewitnesses attributed these phenomena to atmospheric conditions, speculating that the energy released during tectonic movements might interact with the surrounding environment, generating these ghostly apparitions. Others, however, remained skeptical, questioning the reliability of human perception under duress. Despite the uncertainty surrounding their origin, the reports have sparked interest in understanding the potential mechanisms behind these luminous events. Scientific investigations into the relationship between tectonic activity and atmospheric electricity continue, as researchers seek to unravel the mysteries surrounding these rare and striking occurrences. The intersection of geology and atmospheric science remains a fertile ground for exploration, revealing the complexities of Earth's dynamic systems. Understanding light emission involves examining the mechanisms that lead to luminescence, a phenomenon where materials emit light without the involvement of heat. This process can occur in various contexts, including chemical reactions, bioluminescence in organisms, and triboluminescence resulting from the mechanical stress of materials. The energy transitions within atoms and molecules play a crucial role in producing this light. In the context of geological activity, certain minerals exhibit luminescent properties under stress, suggesting a correlation with seismic events. This region, characterized by its tectonic plates, often shows signs of luminescence that precede earthquakes. The release of energy during tectonic shifts may create conditions conducive to the generation of light, as electrons in atoms return to their ground states, emitting photons in the process. Researchers have identified specific minerals such as quartz that exhibit these properties under pressure. The study of these phenomena has led to ongoing investigations into whether luminescence can serve as an indicator of impending seismic activity. Investigations are delving into the conditions under which these lights appear and their possible relation to the buildup of stress along fault lines. Understanding the intricacies of light emission in geological contexts enhances the knowledge of Earth's processes, offering insights into the potential for predicting seismic events with greater accuracy. Witnesses of earthquake lights often describe their experiences with a blend of awe and trepidation. These luminous phenomena evoke a range of emotions, from curiosity to fear, as individuals attempt to comprehend the connection between this eerie illumination and the impending seismic activity. Many report a sense of foreboding, as if the lights are harbingers of disaster, while others find themselves captivated by the beauty of the fleeting glow. The psychological impact of witnessing such events can be profound. For some, these lights serve as a confirmation of their beliefs in the supernatural, or as items of folklore passed through generations. Others may feel a heightened anxiety in relation to natural disasters, fostering a perpetual state of alertness. This heightened awareness can lead to a significant alteration in daily life, as individuals begin to seek out patterns or signs that may indicate future seismic activity. In certain cases, the phenomenon can result in a lasting impression, influencing how individuals perceive their environment and the stability of the ground beneath their feet. Communities that experience these lights often engage in conversations about their meanings, sharing stories that intertwine science and tradition. The intersection of observation and interpretation shapes collective memories, as the fear and fascination surrounding these lights continue to leave an indelible mark on those who witness them. Geography plays a critical role in the occurrence of earthquake lights, as certain regions exhibit a higher frequency of these phenomena. Areas characterized by tectonic activity, such as fault lines and subduction zones, often serve as the backdrop for these mysterious illuminations. Locations like the San Andreas Fault in California, the Nankai Trough in Japan, and the tectonically active regions of Italy have reported sightings. The geological makeup of these zones, including the types of rocks present and their stress points, influences the mechanics behind the generation of light. In the proximity of these fault lines, various factors contribute to the visibility of earthquake lights. Seismic activity, including the buildup of stress along faults, can trigger electrical discharges in the atmosphere. This interaction between geological stress and atmospheric conditions often results in visible light phenomena. Mapping these occurrences helps to establish patterns that may correlate with specific geological events. Surveys and observational studies have documented the geographic distribution of earthquake lights, revealing clusters associated with significant seismic events. The relationship between geography and these luminous phenomena offers insight into the tectonic dynamics at play. Understanding the spatial distribution enhances scientific knowledge and may provide clues for future predictions. The proliferation of urban environments complicates the observation of earthquake lights. Expansive infrastructure, dense populations, and artificial illumination obscure the subtle phenomena that can precede seismic activity. In cities, the myriad sources of light create a pervasive glow that overwhelms the faint luminescence often associated with these pre-quake manifestations. This interference renders the natural phenomena nearly invisible, obscuring valuable data that may otherwise assist in understanding the dynamics of seismic events. In rural settings, where artificial light is less intrusive, the chances of witnessing these elusive lights improve significantly. There, the absence of competing light sources allows for clearer observation and documentation. Communities that remain untouched by urban sprawl serve as critical fields for researchers seeking to capture fleeting instances of these phenomena. The relationship between urbanization and the visibility of earthquake lights underscores a profound challenge. Modern advancements, while fostering technological growth, inadvertently veil some of nature's subtle signals. This conundrum necessitates a re-evaluation of observational strategies, potentially employing advanced imaging technologies capable of filtering out urban light interference. Awareness of this environmental impact is crucial for researchers aiming to deepen their understanding of earthquake lights and to decipher their enigmatic nature in an increasingly urban world. Recognizing the delicate balance between human activity and natural phenomena is essential in fostering future discoveries. Unusual weather patterns often precede seismic activity, sparking intrigue among scientists. These anomalies can manifest as changes in cloud formations, increased electrical activity, or fluctuations in atmospheric pressure. Each observation offers clues, potentially linking the Earth's crust's movements to shifts in the atmosphere. Variations in temperature and humidity levels can also serve as indicators, In certain instances, elevated levels of radon gas have been detected before earthquakes, possibly correlating with geological stress. This region may exhibit a unique convergence of meteorological phenomena, serving as a precursor to tectonic shifts. Researchers have studied these patterns in various locations, yet the results remain inconsistent. While some instances show a clear connection between specific weather changes and seismic events, others reveal no discernible relationship. The variability of atmospheric conditions complicates the ability to draw definitive conclusions. Continued investigation into these unusual occurrences may enhance understanding of earthquake prediction. By examining historical data alongside modern observations, scientists aim to establish a clearer framework for interpreting atmospheric signals. Collaboration across disciplines, including meteorology and geology, plays a crucial role in this ongoing exploration. Insights gained from these studies could lead to improved preparedness and response strategies. The role of electrical discharge phenomena in earthquake lights has sparked considerable interest among researchers. These luminous displays, often observed prior to seismic activity, may arise from the release of electrical energy within the Earth's crust. This energy manifests as light, appearing as glows or flashes in the sky, sometimes described as bluish or white hues. It is believed that the stress and strain on geological materials during tectonic shifts create a piezoelectric effect, whereby certain minerals generate electrical charges. This region, rich in quartz and other piezoelectric materials, serves as a natural laboratory for observing such phenomena. As tectonic plates interact, the intense pressure may lead to the accumulation of these electric charges, resulting in visible discharges. These lights are not universally observed. Their appearances seem to correlate with specific geological conditions and seismic activities, making them a focal point for understanding the complexities of earthquake precursors. Research has begun to explore the mechanisms behind these electrical phenomena, drawing connections to both geological and atmospheric conditions. For instance, variations in humidity and atmospheric pressure may influence the visibility of these lights. Environmental factors, in conjunction with tectonic activity, contribute to the conditions under which earthquake lights may be seen, offering a glimpse into the intricate relationship between the Earth's geology and its atmospheric manifestations. The emergence of earthquake lights raises intriguing questions about their potential link to tsunamis. Observations have documented instances where luminous phenomena appear before seismic events, prompting researchers to explore their correlation with subsequent oceanic disturbances. Tsunamis, generated by undersea earthquakes, can result in significant alterations to shoreline environments and atmospheric conditions. In these scenarios, the sudden release of energy from tectonic shifts may trigger not only seismic waves, but also disturbances in the surrounding atmosphere. The rapid movement of the ocean floor can generate pressure changes, leading to ionization of the air. This process, in turn, may produce visible electrical discharges that manifest as lights. Investigating this relationship requires meticulous study of past events where both phenomena were recorded. Data from seismic records, atmospheric sensors, and eyewitness accounts contribute to understanding this connection. Scientists analyze patterns in both the timing and location of earthquake lights relative to tsunami occurrences. It remains critical to differentiate between genuine atmospheric phenomena and misinterpretations stemming from other sources, such as artificial lights or natural bioluminescence. This ongoing research not only enhances comprehension of tectonic activity, but also offers insights into predictive capabilities. Understanding these relationships could potentially aid in anticipating the risks associated with both earthquakes and the devastating impact of tsunamis. Advanced imaging techniques have emerged as vital tools for documenting the elusive phenomenon of earthquake lights. High-resolution cameras and sensitive imaging sensors capture these transient glows, offering insights into their origins and behaviors. These technologies employ various wavelengths, including infrared and ultraviolet, to observe the lights that may precede seismic activity. Such imaging devices can operate in challenging conditions, often deployed in remote or unstable regions where earthquakes are more likely to occur. Enhanced time-lapse capabilities allow researchers to monitor these phenomena over extended periods, revealing patterns that may correlate with tectonic movements. The resulting data can illuminate the subtle changes in the atmosphere that precede ground shifts. Incorporating machine learning algorithms into the analysis process enhances the understanding of these lights, enabling the identification of patterns that were previously indistinguishable. Through clustering algorithms, researchers can categorize different types of lights, correlating them with specific geological events. Field studies, paired with comprehensive imaging techniques, provide a clearer picture of how these luminous occurrences interact with their environment. This evolving synergy between technology and field research paves the way for a deeper comprehension of the atmospheric conditions associated with seismic events. As knowledge expands, the potential for utilizing these observations to mitigate risks grows increasingly tangible. The influence of media plays a pivotal role in shaping public perception and understanding of phenomena such as earthquake lights. With the advent of digital platforms, reports of these luminous events have gained significant traction, fostering both curiosity and skepticism. Video footage captured during seismic activity often showcases brilliant flashes illuminating the sky, prompting discussions among scientists and the general populace alike. Documentary filmmakers and news outlets strive to present these instances with clarity, aiming to convey the scientific basis behind the lights while acknowledging the enigma that surrounds them. This region, once largely relegated to anecdotal evidence, now finds itself under the lens of rigorous investigation. Each publication, whether online or in print, contributes to a growing archive of documented occurrences, creating a repository of knowledge that transcends geographical boundaries. The collective narratives provided by eyewitnesses are woven into this expanding dialogue, offering a multifaceted view of these phenomena. Scientific communities analyze these reports alongside geological data, seeking correlations that may elucidate the mechanisms at play. This documentation serves not only to validate experiences, but also to encourage further study, all while fostering a sense of communal inquiry into the natural world. The interplay between media representation and scientific exploration lays the groundwork for a deeper understanding of this intriguing phenomenon. Volcanic activity serves as a significant factor influencing the occurrence of earthquake lights. This region, characterized by tectonic instability and molten rock beneath the surface, produces conditions ripe for these elusive luminescent phenomena. Gas emissions, particularly sulfur dioxide, often release intense energy which can interact with the surrounding environment, potentially leading to visible illumination. When magma rises toward the surface, pressure builds within the Earth, creating an intricate interplay of heat and gas. This volatile mixture may result in electrical discharges, manifesting as brilliant flashes of light above the ground. These lights can appear in various forms, including globular or streaks, often preceding seismic activity. The association between volcanic eruptions and earthquake lights has been documented in numerous instances, revealing a pattern that suggests a common origin rooted in geological upheaval. In this context, understanding the connection extends beyond mere observation. It prompts inquiries into the mechanisms that govern these phenomena, such as piezoelectric effects generated by quartz crystals under stress. Investigating the conditions under which these lights emerge offers insights into their predictive capabilities, potentially enhancing our ability to anticipate geological events. The calm yet enigmatic appearance of these lights serves as a reminder of the powerful forces at play beneath the Earth's crust, waiting to reshape the landscape in subtle and profound ways. Historical accounts of earthquake lights reveal a fascinating intersection of natural phenomena and human observation. Documented instances date back centuries, with references appearing in texts from diverse cultures. Ancient civilizations often attributed these luminous occurrences to divine intervention or supernatural forces, illustrating the limited understanding of geological processes at that time. In the early 19th century, reports emerged from regions such as Italy and Japan, where residents noted unusual glows preceding seismic events. These observations sparked interest among scientists and scholars, leading to inquiries into their origins and implications. The phenomenon was initially met with skepticism, as the scientific community struggled to reconcile anecdotal evidence with rigorous empirical research. Analysis of documented cases indicate a recurring pattern, where the lights typically manifest within a narrow time frame before significant seismic activity. The colors observed range from bluish-white to orange hues, often casting an eerie glow over the landscape. Investigations into the potential mechanisms behind these lights have suggested various explanations, including the release of electrical discharges due to tectonic stress. The interplay of geological stresses and atmospheric conditions remains an ongoing area of study. This complex relationship between natural phenomena and human interpretation continues to captivate researchers as they seek to unravel the mysteries surrounding earthquake lights and their implications for understanding seismic behavior. The physics of light provides a fascinating lens through which to explore earthquake lights. This phenomenon is often attributed to wave-particle duality, a fundamental concept in quantum mechanics that describes light as both a wave and a particle. In the context of seismic activity, disturbances in the Earth's crust may generate electrical charges that excite molecules in the atmosphere, leading to the emission of light. These emissions typically occur near fault lines, where tectonic plates interact. Strain accumulation in rock formations can create conditions ideal for the release of energy. When the stored energy is suddenly released, it may create an environment conducive to light production. This luminous display can manifest as a variety of colors and intensities, often observed in the minutes or seconds leading up to seismic events. While these lights remain elusive and poorly understood, they serve as a reminder of the complexities of our planet's geology and its interactions with electromagnetic phenomena. Observations have been recorded across various cultures and geographies, often linked to the anticipation of significant tremors. The pursuit of knowledge regarding earthquake lights not only enhances our understanding of light as a physical entity, but also deepens insights into the dynamic processes occurring beneath our feet. The quest for clarity continues, revealing the intricate webs of nature's behavior. Personal accounts provide valuable insights into the phenomenon of earthquake lights. Witnesses often describe an ethereal glow illuminating the sky in the moments leading up to seismic events. Reports from various regions highlight a connection between these lights and the impending tremors. Observers have noted hues ranging from bluish-white to pale yellow, often seen flickering above the ground or hovering near geological fault lines. In one instance, a resident of a coastal town recounted witnessing a luminous arc just before a significant earthquake. The glow appeared to dance across the horizon, casting an otherworldly light on the surroundings. This sight prompted a sense of urgency among locals, urging them to seek shelter. Another account comes from a rural area, where a farmer described a bright flash illuminating his fields. This unusual light was accompanied by a low rumble, which he later recognized as the precursor to tremors that would soon reshape the landscape. These personal narratives reveal a shared experience, a phenomenon that transcends geographical boundaries. While scientific explanations remain elusive, the consistency of these observations fosters a growing interest in understanding the relationship between seismic activity and atmospheric anomalies. Each testimony adds another layer to the ongoing investigation, bridging the gap between human experience and natural science. Insights gathered from such accounts may illuminate the role of geomagnetism in earthquake light formation. This phenomenon is believed to arise from the interaction between tectonic stress and the Earth's magnetic field. As strain builds in the crust prior to an earthquake, it can produce ionization in the air, leading to the emergence of luminous displays. These lights manifest in various forms, ranging from bluish glows to more vibrant hues. Research suggests that changes in the geomagnetic field may act as a catalyst for these emissions. Fluctuations in magnetic intensity, often occurring during seismic activity, could influence the behavior of charged particles in the atmosphere. This interaction might create transient electrical phenomena, which in turn contribute to the visual displays observed prior to seismic events. In regions of heightened tectonic activity, such as fault lines, the potential for these lights to appear increases. The occurrence is not uniform. Instead, it varies based on local geological conditions and the specific characteristics of each fault system. Scientific investigations into these lights remain ongoing, with researchers employing a range of instruments to monitor and analyze the conditions leading to their emergence. Understanding the intricacies of geomagnetism may provide critical insights into the processes that govern these mysterious phenomena, fostering a deeper comprehension of the Earth's dynamic behavior. Connections between earthquake lights and other anomalous phenomena reveal a curious interplay within the Earth's atmospheric and geophysical systems. These luminous displays often occur alongside seismic activity, suggesting a shared origin. Reports of strange light emissions have also been documented in conjunction with volcanic eruptions and other tectonic disturbances. This relationship indicates potential commonalities in energy release, where stresses in the Earth's crust may generate electromagnetic fields, resulting in visual manifestations that defy conventional understanding. In this region, observations of glowing orbs and flickering lights have been recorded prior to seismic events, leading researchers to explore whether these occurrences serve as precursors. The characteristics of these emissions vary, encompassing hues that range from blue to white, often described as ethereal and unsettling. Investigations into atmospheric electricity reveal that ionization can occur under specific conditions, possibly explaining the appearance of these lights. The parallels drawn between earthquake lights and phenomena such as ball lightning or sprites suggest a broader spectrum of physical processes at play. Each event invites scrutiny as researchers seek to discern patterns and underlying mechanisms that govern these enigmatic displays. This exploration not only enhances the understanding of seismic events, but also opens avenues for uncovering the mysteries of planetary behavior, underscoring the complexity and interconnectedness of Earth's systems. Proposed theories surrounding earthquake lights present a range of explanations that seek to demystify this phenomenon. Some researchers suggest the interaction of geological stress and electrical charges within rocks generates visible emissions. This process, known as piezoelectricity, occurs when quartz and other minerals, commonly found in fault zones, experience deformation. The release of energy may create an electrical discharge, manifesting as luminous phenomena prior to seismic activity. Another explanation involves the release of gases from underground sources. As tectonic plates shift, pressure builds, potentially causing the release of radon or other gases. These emissions, when ignited by natural processes, focus C, may result in glowing lights observable at the surface. This theory highlights the intricate relationship between geological processes and atmospheric conditions, revealing further layers of complexity behind the visual events. Some accounts attribute earthquake lights to plasma formations created by the ionization of air. Friction generated during fault movements may produce electric currents, leading to the formation of plasma that appears as glowing orbs or streaks in the sky. Investigations into these theories are ongoing, with researchers utilizing advanced technology to capture and analyze data in real time. Each proposed explanation contributes to a broader understanding of how seismic activities can influence the environment, fostering a deeper appreciation for the intricate dynamics of the Earth's crust. Earthquake lights have long fascinated researchers and locals alike, emerging as a puzzling phenomenon often observed before seismic events. These luminous displays can cast an eerie glow across the landscape, prompting inquiries into their origin and implications for the surrounding ecosystems. Animals, sensitive to subtle environmental shifts, may react to these lights before tremors occur. Their behavioral changes offer insights into the interconnectedness of geological and biological systems. The presence of these lights could alter the activity patterns of local wildlife. Species that rely on visual cues for navigation or foraging may become disoriented, leading to shifts in their normal behavior. Disruptions in feeding habits can ripple through the food chain, affecting predator-prey dynamics. Additionally, plants may respond to changes in light conditions, potentially influencing growth rates and reproductive cycles. In areas prone to seismic activity, the collective response of species to earthquake lights reflects the intricate relationships within the ecosystem. These interactions contribute to a fragile balance, underscoring the importance of understanding how geological events can extend beyond the ground itself to influence life above it. Studying these phenomena not only deepens knowledge of earthquake precursors, but also highlights the delicate equilibrium that sustains local habitats amid the ever-present threat of the Earth's dynamic forces. Investigations into reports of earthquake lights span various regions, each showcasing unique manifestations of these elusive phenomena. In Japan, witnesses have described glowing orbs hovering above the ground just prior to seismic activity. These luminescent anomalies often appear as pale blue or white lights, flickering with an otherworldly quality, leaving observers both intrigued and unnerved. In California, similar accounts emerge, with residents noting a brief, bright flash illuminating the darkened sky moments before tremors are felt. Such consistent descriptions across diverse locales suggest a common underlying cause. Research teams delve into these occurrences, analyzing environmental conditions and geological settings. In some cases, the presence of certain minerals is noted, indicating a potential link between the geological composition of an area and the generation of these lights. Atmospheric phenomena, including ionization or electrical discharges, are also considered as possible explanations. The interplay of seismic activity and electromagnetic fields creates a complex environment where these lights may emerge. Through meticulous documentation and analysis, scientists strive to understand the mechanisms behind these mysterious glows. Each sighting contributes to a growing body of evidence that may one day clarify their origins. The pursuit of knowledge continues as the relationship between geological events and atmospheric phenomena unveils layers of intricacy within Earth's dynamic processes. Technological advancements have transformed the study of earthquake lights, providing researchers with tools to capture and analyze these elusive phenomena. High-resolution cameras equipped with night vision capabilities allow scientists to document occurrences in real time, revealing subtle changes in luminosity that may precede seismic activity. Satellite imagery further aids investigations by offering a broad perspective of geophysical shifts across vast regions, enhancing the ability to correlate light emissions with tectonic movements. Data collection instruments, such as seismographs, work in tandem with these visual technologies. They measure ground vibrations while also recording the timing and intensity of light phenomena. This synchronization of data offers a more comprehensive understanding of the sequence of events leading to an earthquake. Enhanced computational modeling techniques analyze the gathered information, identifying patterns and potential triggers associated with these mysterious lights. Collaboration across disciplines has become increasingly important. Physicists, geologists, and atmospheric scientists converge to share insights, posters, and tights, fostering a more nuanced understanding of the interactions between the Earth's lithosphere and its atmosphere. Publicly accessible databases now enable citizen scientists to contribute observations. Immersive or continuous publicly accessible databases now enable citizen scientists to contribute observations immersive, broadening the scope of research beyond traditional academic settings. For this intersection of technology and science not only deepens comprehension of earthquake lights, but also paves the way for future predictive capabilities in seismology. The interaction of seismic waves and atmospheric conditions reveals a complex relationship that remains a focal point of ongoing research. When tectonic plates shift, they generate seismic waves that propagate through the Earth's crust, creating vibrations that can influence the atmosphere above. These waves can induce changes in the electrical properties of the air, potentially leading to the generation of unusual light phenomena. In Frenice region, observations indicate that specific atmospheric conditions, such as humidity and temperature fluctuations, may enhance the visibility of these lights. Elevated moisture levels can increase ionization in the air, contributing to a more pronounced display. Notably, the presence of certain minerals and gases released during tectonic activity may also play a role in this process, affecting both the composition of the air and the characteristics of the light observed. Research continues to explore the mechanisms behind this phenomenon, as the interplay of seismic activity and atmospheric conditions offers insights into the fundamental processes governing our planet. While the exact nature of the lights remains elusive, their correlation with seismic events suggests a deeper connection between the Earth's interior and its atmosphere. Understanding this connection may eventually lead to advancements in predicting not only earthquakes, but also the atmospheric anomalies that accompany them, enhancing safety and preparedness for future seismic events. Evidence of earthquake lights presents a fascinating intersection of geology and atmospheric science. These luminous phenomena, reported before significant seismic activity, have puzzled researchers for decades. Observations describe pale glows, flickering orbs, and even bluish flames that emerge from the ground or sky. Such occurrences may be linked to the release of gases from tectonic stress, influencing the ionization of air molecules. Modern science employs various analytical tools to study these lights, including satellite imagery and ground-based sensors. Data collected from historical events contribute to a growing database, enabling more thorough examination of the conditions under which these lights manifest. The occurrence of earthquake lights often aligns with the buildup of tectonic strain, suggesting a complex interplay between geological processes and atmospheric phenomena. In some cases, eyewitness accounts correlate with seismic predictions immersive, reinforcing the need for comprehensive research. The exploration into these luminous events not only broadens the understanding of seismic activity, but also opens avenues for interdisciplinary collaboration. Geologists and atmospheric scientists work together, aiming to decode the signals emitted prior to earthquakes, potentially forming a predictive model that integrates both geological and atmospheric data. Such integration could redefine preparedness strategies, equipping communities with the knowledge necessary to respond to impending seismic events with greater efficacy. The existence of earthquake lights has sparked significant debate among scientists. Observations of anomalous glowing phenomena preceding seismic events have been documented for centuries. Yet the scientific community remains divided on their authenticity and origins. Some researchers assert that these lights are merely atmospheric electrical discharges resulting from tectonic stress and the release of gases. Others propose alternative theories, suggesting that the lights could signify a unique interaction between the Earth's crust and its electromagnetic fields. In certain regions, witnesses have reported witnessing these luminous displays in various colors, ranging from bluish-white to orange. Descriptions often detail their sudden appearance, followed by the onset of tremors, prompting further investigation into the correlation. Skeptics argue that such accounts may be influenced by psychological factors or misinterpretations of natural phenomena, like lightning or auroras. In laboratory settings, attempts to replicate the conditions that lead to these lights have shown some promise, yet the complexity of the underlying mechanisms remains elusive. Ongoing studies continue to explore the relationship between tectonic activity and atmospheric phenomena. This region's geological features, combined with the interplay of electrical forces, may hold the key to understanding these enigmatic occurrences. The quest for clarity persists amid evolving hypotheses, as researchers strive to bridge the gap between observation and theory, seeking a definitive explanation for these mysterious glows. Citizen science has emerged as a vital tool in the documentation of earthquake lights. Individuals in various regions have taken it upon themselves to report sightings, contributing valuable data that may otherwise remain unnoticed. Through the careful observation of these phenomena, accounts from everyday witnesses offer insights that complement the scientific community's efforts. This grassroots involvement generates a rich repository of information, enabling researchers to analyze patterns and correlations associated with seismic activity. Reports often include precise descriptions of the light's color, intensity, and duration, providing contexts that may be crucial for understanding their origins. Such contributions create a mosaic of experiences, revealing the diverse manifestations of these luminous occurrences. Many witnesses describe the lights as shimmering, flickering, or even appearing as arcs, each unique observation adding depth to the collective understanding. In this collaborative environment, technology plays a significant role. Mobile applications and online platforms facilitate the sharing of sightings in real time, enhancing the speed and efficiency of data collection. Furthermore, social media networks connect individuals, fostering a community of enthusiastic observers who exchange information and theories. While the phenomenon remains enigmatic, the engagement of citizen scientists cultivates a collaborative effort to demystify earthquake lights, amplifying the voices of those who experience them firsthand. This partnership between experts and the public is instrumental in advancing knowledge within the field of atmospheric science. Future research directions in earthquake light studies are poised to expand significantly, Investigations will likely delve deeper into the mechanisms behind these phenomena, aiming to discern the precise conditions that give rise to luminous displays. Scientists may explore the role of geological stress and the release of gases from the Earth's crust, seeking correlations between seismic activity and the observed light emissions. Increased collaboration with seismologists and geophysicists will contribute to a more comprehensive understanding, utilizing advanced imaging techniques and high-resolution sensors. Researchers intend to capture these lights across various seismic events. This multifaceted approach may lead to the identification of specific geological formations that are more prone to producing such phenomena. Data collection will become more systematic, allowing for rigorous analysis of occurrences worldwide. The integration of artificial intelligence and machine learning could streamline the identification of patterns in historical data, enhancing predictive capabilities related to these light spans. Field studies will become essential, with dedicated teams observing and documenting events in real time. Such efforts aim to bridge the gap between observation and theory, fostering a clearer picture of how these lights manifest. Detecting earthquake lights presents a series of challenges that complicate the understanding of their occurrence. The elusive nature of these phenomena often results in anecdotal evidence rather than systematic observation. This region, where these lights are reported, varies widely, leading to inconsistencies in documentation. Factors such as atmospheric conditions, local geography, and the observer's vantage point introduce significant variables. These lights often appear moments before seismic activity, yet the exact mechanism that triggers their emergence remains unclear. Some theories suggest that electrical charges generated by tectonic stress may cause ionization in the atmosphere, producing a luminescent effect. This possibility necessitates an interdisciplinary approach, merging geology with atmospheric science to explore the intricate relationships between these disciplines. Developing reliable instruments for detection is another hurdle. Existing technologies may not capture fleeting phenomena effectively, particularly in remote areas where earthquakes and lights are most prevalent. This gap restricts the ability to gather comprehensive data during seismic events. In addition, the subjective interpretation of what constitutes an earthquake light complicates analysis. Variations in color, intensity, and duration may lead to differing classifications, creating further ambiguity. The ongoing quest to demystify these phenomena continues, driven by the need for clarity in the face of enigmatic observations. As research progresses, the hope remains to uncover the underlying mechanisms governing these unusual emissions. Science and förthioniker de frågskostnad för warrants enforced safety. Communities situated in seismically active regions often experience heightened anxiety, a byproduct of uncertainty surrounding natural disasters. The emergence of earthquake lights has led to increased public interest and concern, prompting discussions around preparedness and risk mitigation. Educational initiatives have arisen, aiming to inform residents about both the phenomena and the seismic hazards they may face. Workshops and community meetings serve as platforms for sharing knowledge, empowering individuals to recognize potential warning signs. This proactive approach cultivates a sense of unity among residents, fostering resilience in the face of uncertainty. Emergency services and local governments are adapting their strategies to incorporate the possibility of earthquake lights into their response protocols. This integration reflects an evolving understanding of seismic behavior, where the mysterious glow could serve as an additional indicator of impending events. Research into these emissions is gradually shaping public policy, encouraging investment in seismic monitoring technology. Such advancements aim to enhance early warning systems, while earthquake lights remain a subject of ongoing research. Comparisons to phenomena associated with other natural disasters reveal intriguing parallels. Lightning, for instance, often accompanies thunderstorms, revealing the relationship between electrical activity and atmospheric disturbances. In a similar vein, it appears that these luminous manifestations might emerge due to the intense stress and strain within the Earth's crust prior to seismic occurrences. Volcanic eruptions also exhibit unique optical phenomena, including glowing lava and incandescent gas emissions. Both earthquakes and volcanic activity can generate light due to the interaction of geological processes with the atmosphere. This region, marked by tectonic movement, can produce natural displays that precede or accompany these powerful events. Summerciphalazem, while primarily characterized by their immense waves, can likewise trigger electrical disturbances. Reports of electromagnetic anomalies preceding tsunami events evoke a sense of interconnectedness among various natural disasters. These observations suggest that the Earth's systems are intricately woven, where one event may herald another. Scientific inquiry into these associations continues to develop, with researchers meticulously documenting occurrences of lights and other phenomena linked to seismic activity. The search for patterns in these observations holds promise for understanding the underlying mechanisms driving both earthquake lights and other natural disasters, potentially leading to enhanced prediction capabilities in the future. Research into the biophysical mechanisms behind human perception of earthquake lights reveals complex interactions between environmental stimuli and neurological responses. These phenomena often manifest as luminous displays prior to seismic activity, with observers describing colors ranging from bluish-white to reddish hues. Such variations may be influenced by atmospheric conditions and the properties of the materials involved in the seismic event. Electromagnetic fields generated by tectonic stress could interact with the ionosphere, leading to the excitation of gas molecules. This excited state may produce visible lights, observable under specific conditions. Human perception of these colors relies on the functioning of the retina, where specialized photoreceptor cells respond to varying wavelengths. The brain processes this visual information, integrating it with sensory input from the surrounding environment. The psychological aspect of perceiving these lights introduces further layers of complexity. Emotional states, cultural beliefs, and previous experiences shape interpretations of unusual phenomena. In some regions, such occurrences have been woven into local folklore, impacting the way communities respond to potential seismic threats. Investigating the intersection of atmospheric science and neurological function continues to shed light on this captivating phenomenon. By understanding how these luminous displays are perceived, scientists pave the way for future research that may enhance public awareness and preparedness for seismic events. International collaboration plays a crucial role in the advancement of earthquake light research. Various countries contribute unique datasets, methodologies, and expertise, enriching the collective understanding of this phenomenon. Researchers from diverse fields, such as geology, physics, and atmospheric sciences, join forces to investigate the mechanisms underlying these luminous occurrences. Their combined efforts facilitate the identification of common patterns and anomalies across different tectonic settings. Joint research initiatives often utilize advanced technologies such as satellite imagery and ground-based observation networks to monitor seismic activities and their associated atmospheric phenomena. These collaborations enhance data reliability and allow for a comprehensive analysis of earthquake lights across multiple geographical regions. The pooling of resources and knowledge not only accelerates the pace of discovery, but also fosters a culture of scientific inquiry, that transcends borders. Conferences and workshops serve as platforms for scientists to share findings and discuss methodologies, promoting a unified approach to studying these elusive lights. The establishment of global databases compiles reports and observations, creating a valuable resource for scholars and practitioners alike. As understanding deepens, the implications for public safety and preparedness become clearer, leading to improved prediction models that could potentially save lives. Through such endeavors, the international scientific community continues to unravel the mysteries surrounding these enigmatic phenomena. The integration of drones and remote sensing technology has significantly advanced the study of earthquake lights. These unmanned aerial vehicles, equipped with high-resolution cameras and specialized sensors, facilitate the collection of data in areas that are often challenging to access. This capability allows researchers to observe environmental changes in real time, observing anomalies that may precede seismic events. Aerial surveys can capture visual evidence of light emissions associated with tectonic stress. Thermal imaging devices mounted on drones detect temperature fluctuations, which might indicate geological activity. These observations provide a more comprehensive view of the atmospheric conditions surrounding fault lines. Enhanced data collection methods contribute to a growing database of potential precursors to earthquakes. In tandem with satellite observations, these technologies offer a unique perspective on regional geological dynamics. The synergy between drone capabilities and remote sensing creates opportunities for analyzing patterns over time, revealing correlations that were previously obscured by the limitations of ground-based studies. This region, characterized by its intricate geological makeup, becomes a focal point for researchers aiming to understand the relationship between tectonic movement and atmospheric phenomena. As investigations continue, integrating these technological advancements may lead to improved predictive models. The potential for enhanced understanding of earthquake lights remains, illuminating a path toward better preparedness and resilience in vulnerable communities. Statistical analyses over time reveal patterns in the occurrence of earthquake lights, suggesting a correlation with seismic activity. Data collected from various regions indicate that these luminous phenomena are most frequently reported in the moments leading up to a seismic event, often within a time frame of several hours. This region, characterized by tectonic plate movements, has produced numerous cases of lights appearing with varying intensities and colors, ranging from bluish to whitish hues. Quantitative studies focus on the frequency and distribution of reports, allowing researchers to identify hotspots where these occurrences are more prevalent. In some instances, the analysis reveals a significant increase in sightings prior to major earthquakes, providing a potential predictive element in monitoring seismic behavior. This correlation prompts further investigation into the underlying mechanisms responsible for such lights, including piezoelectric effects in quartz and other geological materials. Temporal analysis also highlights the clustering of reports around specific fault lines, suggesting localized geological features may play a role. By compiling and comparing historical data across diverse global regions, researchers aim to establish a comprehensive database that encompasses various factors, including geological composition and environmental conditions. This ongoing work contributes to the broader goal of enhancing early warning systems and increasing public awareness of natural phenomena associated with seismic events. The psychological phenomena surrounding light-related anxiety in earthquake zones manifests as a response to the unpredictable nature of seismic activity. Residents in these regions often report heightened levels of unease, particularly when observing unusual luminescent displays in the atmosphere. These lights, often perceived as harbingers of impending tremors, trigger a sense of foreboding, causing individuals to remain in a constant state of alertness. This anxiety can lead to behavioral changes. Individuals may develop avoidance strategies, steering clear of areas where such phenomena are frequent. The uncertainty surrounding the correlation between these lights and earthquakes fuels speculation, further intensifying the psychological impact. It becomes a cycle, as the fear of potential disaster intertwines with the experience of witnessing these enigmatic glows. Studies indicate that the emotional response to light phenomena may vary among different demographics. Some might interpret the lights as warnings or messages, while others view them as mere coincidences. This divergence in perception reflects broader cultural beliefs and personal experiences, shaping how communities respond to seismic threats. Inhabitants often engage in discussions about their sightings, creating a shared narrative that reinforces the collective anxiety. This social reinforcement solidifies the belief that the lights are significant, perpetuating the emotional landscape of fear that envelops these communities. Such dynamics illustrate the profound interplay between geological events and human psychology, highlighting the intricate relationship between environment and emotional response. The role of education in understanding earthquake lights cannot be overstated. Accessible information regarding these phenomena fosters awareness and encourages scientific inquiry. Educational institutions have increasingly integrated discussions of natural disasters into their curricula, promoting a comprehensive understanding of both the science behind these lights and their historical context. This knowledge prepares communities to respond more effectively to geological events. In classrooms and research settings, students engage with scientific principles such as seismology and atmospheric physics. Through this engagement, they learn how certain conditions, including tectonic stress and electrical activity, may contribute to the manifestation of these luminous phenomena. Laboratory experiments and simulations deepen comprehension, allowing learners to visualize complex interactions within the Earth's crust. Public outreach initiatives also play a vital role. Workshops, seminars, and informational campaigns equip individuals with the tools to recognize and interpret earthquake lights. As communities develop a shared understanding, the collective response to seismic events becomes more informed and measured, reducing panic and misinformation. Investing in education on this subject strengthens resilience, empowering people to approach potential disasters with a calm, analytical mindset. By embracing scientific inquiry and fostering a culture of learning, societies can better navigate the unpredictable nature of their environment, enhancing both safety and awareness in the face of geological uncertainty. The interplay between geological phenomena and urban development necessitates a re-evaluation of infrastructure in seismically active areas. In regions prone to earthquakes, the implications for city planning extend far beyond aesthetic considerations. This environment demands robust engineering practices that prioritize resilience against potential seismic events. Buildings and structures require design modifications to withstand the forces generated by ground movement, utilizing materials and techniques specifically tailored to absorb and dissipate energy. Proactive measures include the integration of flexible foundations and the use of reinforced materials that can endure stress without collapsing. Urban planners must also consider the strategic placement of essential services, such as hospitals and emergency response centers, in locations less susceptible to damage. Furthermore, the establishment of open spaces can provide necessary refuge during and after seismic occurrences, minimizing risks to human life. Infrastructure must be regularly assessed and retrofitted to align with evolving seismic research findings. This ongoing process ensures that societal resilience is maintained, allowing communities to recover more efficiently after an event. Public awareness campaigns contribute to preparedness, educating citizens about safety protocols and emergency plans through diligent planning and engineering foresight. It is possible to create urban environments that coexist with the geological forces that shape them, fostering a safer future amidst inherent uncertainties. The relationship between environmental factors and seismic activity extends beyond geological formations. Observations indicate that climate change may influence the frequency and intensity of earthquakes, creating conditions where the emergence of earthquake lights could become more prevalent. This phenomenon, characterized by luminous glows in the sky preceding seismic events, is often attributed to the release of electrical charges in the Earth's crust. Higher temperatures and altered precipitation patterns can lead to increased pressure on fault lines, with melting glaciers and rising sea levels contributing to the destabilization of the Earth's surface. As water infiltrates fractures in the rock, it may enhance the likelihood of tectonic movement, generating the potential for these enigmatic lights. Thus, one-surface in Fleig displays, often described as fleeting and unpredictable, serve as a reminder of the interconnectedness of Earth's systems. Scientists continue to explore the mechanisms behind these illuminations, seeking to understand the correlation between environmental shifts and seismic activity. The implications of climate change extend into the realm of human safety and preparedness. Understanding how environmental factors may augment seismic risks underscores the necessity for adaptive strategies. By recognizing these intricate relationships, society can better prepare for the challenges posed by an evolving climate, ensuring that infrastructure and communities are resilient in the face of both visible and hidden threats. The relationship between earthquake lights and other geophysical signals offers a fascinating glimpse into the interplay of natural phenomena. These luminous phenomena often precede seismic events, suggesting an underlying connection to tectonic activity. Various studies have indicated that alterations in the Earth's crust can generate electromagnetic fields, which may manifest as these mysterious lights. Such emissions have been recorded in conjunction with changes in groundwater levels and gas emissions, reflecting the interconnectedness of geological processes. Pockets of gas, such as radon, may accumulate near fault lines, potentially contributing to the conditions that foster the appearance of lights. This region of the Earth's crust, under immense pressure, can release energy in multiple forms, revealing a complex communication network within the planet. The presence of these lights has prompted researchers to explore their potential as precursors to earthquakes. Observations from historical events highlight their sporadic nature, often appearing in various colors and intensities, depending on local geological characteristics. In some instances, they have manifested days to hours before significant tremors, offering invaluable insight into the Earth's behavior. Understanding these signals not only enriches scientific knowledge, but also enhances predictive models. It emphasizes the need for continued investigation into the subtle cues emitted by the Earth, which may hold the key to foreseeing seismic activity. Neural mechanisms play a crucial role in interpreting the experiences associated with earthquake lights. Sensory processing occurs through complex pathways in the brain, where visual stimuli are analyzed and integrated. When these unusual phenomena manifest, they might trigger various cognitive responses, leading individuals to interpret the lights in diverse ways. Certain regions, such as the occipital lobe, are responsible for visual perception, allowing the brain to identify the glow simultaneously. The limbic system can invoke emotional reactions, creating a sense of unease or curiosity. This interplay between sight and emotion can influence how individuals prepare for potential seismic events. intertwining physiological responses with psychological perceptions. Reports suggest that not all observers interpret these lights uniformly. Variability in personal experiences and cultural backgrounds can shape one's understanding and reaction to the phenomena. Additionally, the brain's ability to form connections between prior knowledge of earthquakes and the unexpected visual display may lead to heightened awareness or anxiety. Research continues to explore the neural underpinnings of this phenomenon, seeking to unravel how these lights are processed and perceived. Understanding the brain's role not only enhances scientific knowledge, but may also contribute to improved public safety measures. Tapping into these insights may inform public policy aimed at enhancing earthquake preparedness. Implementing regulations that prioritize infrastructure resilience becomes essential in regions prone to seismic activity. Building codes must be evaluated and updated to ensure structures can withstand the forces unleashed by tectonic shifts. This region, characterized by its geological volatility, requires a proactive approach to development, minimizing the risks posed to inhabitants and critical infrastructure. Emergency response protocols necessitate careful consideration, incorporating lessons learned from past seismic events. Training programs for first responders should include specific scenarios related to earthquake lights, as this phenomenon may serve as an early warning signal. Awareness campaigns can educate communities about the potential indicators of seismic activity, fostering a culture of readiness and response. Incorporating technology into disaster management systems enhances communication and provides real-time updates during seismic events. Geographic information systems can pinpoint areas most at risk, ensuring resources are allocated effectively. Collaborative approaches between governmental agencies and local communities strengthen the framework for preparedness, ensuring that all stakeholders participate in the planning process. Funding for research into earthquake prediction and the phenomena associated with seismic events remains critical. This investment not only aids in understanding potential warning signs, but also contributes to the development of innovative solutions to mitigate the impacts of future earthquakes. The phenomenon of earthquake lights presents an intriguing intersection between geological activity and atmospheric conditions. These luminous displays, often described as bluish or white glows, emerge in the moments leading up to seismic events. Observations indicate that they may result from the release of electrical energy from stressed rock formations, offering a potential visual precursor to earthquakes. Global seismic monitoring efforts are increasingly incorporating the study of these lights, recognizing their potential significance in enhancing predictive models. Advanced sensors and satellite imagery are employed to document and analyze occurrences of earthquake lights across various regions. This data not only aids in correlating the phenomenon with seismic activity, but also offers insights into the geological processes at play beneath the Earth's surface. Continued research into earthquake lights may reveal patterns and conditions that precede seismic events, informing early warning systems. Understanding the precise mechanisms behind these luminous displays could lead to improved risk assessment models, contributing to public safety measures in earthquake-prone areas. As investigations into these phenomena advance, the connection between atmospheric phenomena and geological processes becomes clearer, emphasizing the importance of interdisciplinary approaches in understanding complex natural events. The study of earthquake lights stands as a testament to the remarkable interplay between Earth's various systems, inviting further exploration into their implications for both science and society. Skepticism around earthquake lights persisted for decades, often dismissed as mere folklore or optical illusions. Early observations, recorded as far back as the 18th century, presented a myriad of interpretations ranging from natural phenomena to supernatural explanations. This skepticism was rooted in the ambivalence of those who sought empirical evidence, leading to a fragmented understanding of these luminous occurrences. With the advent of modern technology, the investigation into these phenomena began to gain traction. Advanced imaging techniques and sensitive instrumentation enabled researchers to capture these elusive glows, providing concrete data to support their existence. Notable case studies emerged, detailing the correlation between seismic activity and light phenomena, further bridging the gap between anecdotal accounts and scientific discourse. Gradually, acceptance grew within the scientific community. Collaborative research efforts refined theoretical models, identifying various mechanisms responsible for the observed lights. These mechanisms include piezoelectric effects and the excitation of gas in the atmosphere. Each new discovery contributed to a more nuanced understanding of how such lights might manifest in relation to tectonic shifts. Today, earthquake light research remains a vibrant field, bridging geology, physics, and atmospheric science. As understanding deepens, it holds the potential not only to enhance predictive methodologies, but also to inform public policy on disaster preparedness and response strategies, reflecting the profound connection between human experience and the earth beneath. Challenges in earthquake light research persist, primarily stemming from the elusive nature of these phenomena. The transient glow often occurs moments before seismic events, making it difficult to study within controlled environments. Researchers face limitations in data collection, as eyewitness accounts are frequently anecdotal, lacking rigorous scientific validation. The need for advanced observational techniques is paramount. The implementation of high-resolution imaging technology and enhanced seismic monitoring systems could provide invaluable insights into this elusive glow. Opportunities arise from interdisciplinary collaboration by integrating geology, atmospheric science, and electromagnetic studies. A more comprehensive understanding of the underlying mechanisms can be developed. Improved models that simulate the conditions leading to these lights may yield predictive capabilities that extend beyond earthquakes, perhaps even encompassing volcanic activity or other geological phenomena. Public engagement represents another avenue for progress. Raising awareness about earthquake lights could foster community involvement in research initiatives, encouraging citizens to report sightings and contribute to data gathering. As these efforts unfold, the synthesis of citizen science with academic inquiry may enrich the dataset, creating a more robust framework for analysis. Investigations into earthquake lights bring together various fields, including geology, atmospheric science, and physics. This multidisciplinary approach allows researchers to examine the phenomena from multiple angles, enhancing the understanding of the conditions under which these luminous events occur in specific regions where seismic activity is prevalent. Atmospheric conditions seem to play a crucial role. The interaction between tectonic movements and electrical fields generated by stress in the Earth's crust may contribute to the formation of these lights. Accounts reveal that the lights often manifest as bright flashes or glowing orbs, appearing moments to days before seismic events. These observations, although anecdotal, underscore the potential for a deeper connection between geological processes and atmospheric phenomena. Scientists analyze the timing and characteristics of these sightings, seeking correlations with seismic data. In laboratory settings, experiments simulate the conditions believed to generate these lights, focusing on piezoelectric effects and gas discharge phenomena. Such controlled studies offer insights into the underlying mechanisms that might be responsible for these strange illuminations. The integration of observational data with experimental findings fosters a better understanding of how and why these lights occur. The role of art and media in representing these phenomena reflects a deep-seated human fascination with the unknown. Various artistic interpretations convey a sense of wonder, capturing the ethereal glow that some witnesses describe. Visual artists often depict these lights in ways that evoke mystery and intrigue, using vibrant colors to suggest the surreal nature of the event. Photography and digital media serve as platforms that allow for the documentation of fleeting moments, bringing attention to the elusive spectacle. Documentaries and educational programs contribute significantly to public understanding. Through interviews with scientists and eyewitnesses, these narratives explore the intersection of art and science. They highlight personal experiences and emotional responses, framing the lights within a broader context of seismic activity. This blending of disciplines creates a richer dialogue surrounding the phenomenon, drawing in both skeptics and believers. Literature further expands on the theme, where authors weave narratives that explore the psychological impact of witnessing such lights. Fictional accounts often elevate the experience, placing characters in situations that challenge their understanding of reality. In this way, art and media shape perceptions, fostering curiosity while also invoking a sense of caution regarding the forces of nature. This multifaceted engagement with the phenomenon emphasizes its significance not just as a scientific curiosity, but also as a profound element of human experience. Metano's involvement plays a crucial role in the study of earthquake lights. Local residents often become the first observers, noting unusual phenomena in the sky prior to seismic events. These observations can be critical in gathering data, as their proximity to the events provides a unique perspective. Engaging communities fosters a sense of ownership over local knowledge, encouraging individuals to share their experiences and insights. Training programs for local volunteers aim to equip them with the skills needed to document sightings accurately. Observers learn to distinguish between natural atmospheric phenomena and potential earthquake lights, enhancing the reliability of their reports. Collaboration with scientists creates a network of information, allowing researchers to analyze patterns and correlations. This synergy not only leads to the gathering of valuable data, but also strengthens community resilience. Residents who understand the signs of impending seismic activity can better prepare themselves and their families. The shared experience of monitoring these lights builds a collective awareness, transforming individual observations into a communal resource. As reports accumulate, patterns emerge, revealing potential correlations between specific conditions and the occurrence of these lights. This collaborative effort highlights the ethical complexities faced by scientists and journalists alike. Accurate reporting of phenomena such as earthquake lights requires a careful balance between scientific inquiry and the potential consequences of disseminating information. The urgency to inform the public about emerging discoveries must be weighed against the risk of causing undue panic or misinformation. It is essential for researchers to communicate their findings with clarity, ensuring that the nature of earthquake lights is understood within a scientific context. Misinterpretation can lead to fear or skepticism, particularly when the phenomenon remains enigmatic. Ambiguities surrounding the origins and reliability of these lights necessitate a cautious approach to public discourse. In this region, where seismic activity is prevalent, the anticipation of an earthquake can heighten anxiety. Responsible reporting entails not only conveying the existence of these lights, but also contextualizing them within the broader spectrum of earthquake science. This responsibility extends to media outlets, which play a pivotal role in shaping public perception. By providing balanced coverage, they ensure that the public remains informed without succumbing to sensationalism. The dialogue between scientists and the media is crucial, fostering a shared understanding that prioritizes education over alarm. Engaging the public with accurate information cultivates a well-informed society, capable of navigating the uncertainties associated with seismic phenomena. The prevailing debate surrounding earthquake lights often centers on the nature and origins of these luminous phenomena. Observations have been reported prior to significant seismic events, leading to a mixture of intrigue and skepticism. Some attribute the glow to geological processes, suggesting that the movement of tectonic plates generates electrical charges that manifest as light. This theory posits that stress accumulation within the Earth's crust can release energy in the form of visible electromagnetic radiation. Skeptics, however, point to the myriad of alternative explanations, ranging from atmospheric ionization to electrical discharges caused by human activity. These alternative theories complicate the understanding of earthquake lights as they challenge the notion of a direct correlation between this phenomenon and impending seismic activity. Instances of lights appearing without subsequent earthquakes further fuel the debate, prompting discussions about the reliability of eyewitness accounts and the influence of environmental conditions. Scientific inquiry continues to examine these enigmatic lights. Research relies on a combination of observational data and experimental studies to disentangle the true nature of the phenomenon. As studies progress, the urgency to educate the public on the subtleties of these phenomena remains paramount. Clarity and accurate information can bridge the gaps in understanding, leading to a greater appreciation of the complexities inherent in Earth's geophysical processes. Historical records reveal a fascinating evolution in the understanding of earthquake lights, initially dismissed as folklore or mere myth. These luminous phenomena began to attract scientific scrutiny in the late 19th century. Observers reported unusual glows during seismic events, prompting inquiries into their possible causes. Early theories suggested that electrical discharges from the Earth could account for the sightings, yet a lack of empirical evidence limited acceptance. The mid-20th century marked a pivotal shift. Geophysicists began to document instances of these lights more rigorously, leading to a growing acknowledgement of their potential links to seismic activity. The phenomenon was increasingly framed within the context of piezoelectric effects, where stressed materials generate electrical charges. Such insights allowed researchers to systematically analyze the conditions under which these lights appeared. By the late 20th century, advancements in observational technology provided clearer data. Satellite imagery and ground-based sensors captured lights associated with earthquakes, offering a more robust framework for understanding their origins. This period saw a transition from skepticism to a recognition of their significance, prompting further investigations into the geological conditions preceding seismic events. Current research continues to refine the understanding of earthquake lights, exploring their possible connections to tectonic stress and gas emissions. This ongoing inquiry reflects the dynamic nature of scientific knowledge, illuminating the intricate relationships between geological processes and atmospheric phenomena. Insights gained from observing these lights have led to a deeper understanding of the natural world. This phenomenon has inspired scientists to explore the underlying mechanisms that could explain their occurrence. The correlation between seismic activity and the appearance of luminescent displays in the atmosphere has prompted inquiries into piezoelectric effects in crystalline structures found in the Earth's crust. The presence of certain minerals, when subjected to stress, may generate electric fields that manifest as luminous emissions. Research into this relationship continues to evolve, with interdisciplinary collaborations merging geophysics, atmospheric science, and materials science. Investigations have revealed that these lights are not merely an optical illusion, but potentially a harbinger of seismic events, offering valuable insights into earthquake prediction. The enigmatic nature of these lights has also captured the imagination of researchers and the public alike. Their unpredictable appearance lends a certain mystique, urging scientists to refine their methodologies and expand their observational arrays. Ground-based monitoring combined with satellite observations is becoming increasingly prevalent in these studies. In regions prone to seismic activity, communities are beginning to document sightings of these lights, contributing anecdotal evidence to the growing body of research. Each observation serves as a stepping stone towards a more comprehensive understanding of the intricate interplay between the Earth's movements and the atmospheric responses they provoke. The legacy of earthquake light research continues to unfold, revealing layers of complexity within Earth's geological and atmospheric systems. These luminous phenomena, often seen just before seismic events, challenge existing scientific paradigms and invite further exploration. The desire to understand their origins and mechanisms has sparked interdisciplinary collaboration among geophysicists, atmospheric scientists, and even historians, each contributing unique perspectives to this enigmatic subject. Innovative technologies are being developed to capture and analyze these lights in real time. Instruments equipped with advanced imaging capabilities and spectroscopic tools are deployed in seismic regions, aiming to gather data that has eluded researchers for decades. This technological evolution promises to enhance the quality of observations, providing the essential data needed for rigorous analysis. The future of earthquake light research may also lead to practical applications. Improved predictive models could emerge, potentially offering insights that transform how societies prepare for seismic threats. The integration of atmospheric and geological data could yield breakthroughs in understanding not only earthquake lights, but also broader phenomena related to Earth's dynamic systems. As exploration continues, each discovery adds to the nuanced narrative of how the planet communicates through light. This journey reflects humanity's enduring quest to decipher the natural world, fostering a deeper connection to the forces that shape existence. Exploration of earthquake lights unveils a wealth of literature, providing both enthusiasts and scholars with rigorous insights into this phenomenon. Numerous studies document various instances where luminous displays have been reported prior to seismic events. These accounts span multiple cultures and geographical locations, deepening the understanding of the phenomenon's historical context. Key texts include Earthquake Lights, a review of the literature by Robert R. Wesson, which consolidates findings from various regions, detailing the conditions under which these lights are observed. Additionally, The Lights of the Earthquake by David A. Estambons offers a scientific perspective, integrating data from physical observations with theoretical frameworks. Research articles in journals such as Seismological Research Letters and Geophysical Research Letters provide peer-reviewed studies focusing on the geophysical mechanisms that may explain these occurrences. The intersection of geophysics and atmospheric sciences is examined in detail, revealing potential links between tectonic activity and atmospheric electrical phenomena. Further, the work of scientists like Yoichi Hayakawa explores the electromagnetic emissions preceding earthquakes, contributing to a more nuanced understanding of how these lights might be generated. This body of literature invites ongoing inquiry, fostering a collaborative environment for future research, as the quest to unravel the mysteries surrounding earthquake lights continues to evolve.